Section 5. The Atomic Bombings of Hiroshima and Nagasaki. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, visit LibriVox.org. The Atomic Bombings of Hiroshima and Nagasaki by the Manhattan Engineer District, June 29, 1946. Section 5, including characteristics of the damage caused by the atomic bombs, calculations of the peak pressure of the blast wave, long-range blast damage, ground shock, shielding or screening from the blast, and flash burn. Characteristics of the damage caused by the atomic bombs. The damage to man-made structures caused by the bombs was due to two distinct causes. First, the blast, or pressure wave, emanating from the center of the explosion, and second, the fires, which were caused either by the heat of the explosion itself or by the collapse of buildings containing stoves, electrical features, or any other equipment which might produce what is known as a secondary fire, and subsequent spread of these fires. The blast produced by the atomic bomb has already been stated to be approximately equivalent to that of 20,000 tons of TNT. Given this figure, one may calculate the expected peak pressures in the air at various distances from the center of the explosion, which occurred following detonation of the bomb. The peak pressures, which were calculated before the bombs were dropped, agreed very closely with those which were actually experienced in the cities during the attack, as computed by Allied experts in a number of ingenious ways after the occupation of Japan. The blast of pressure from the atomic bombs differed from that of ordinary high explosive bombs in three main ways. A. Downward thrust. Because the explosions were well up in the air, much of the damage resulted from a downward pressure. This pressure, of course, most largely affected flat roofs. Some telegraph and other poles immediately below the explosion remained upright, while those at greater distances from the center of damage, being more largely exposed to a horizontal thrust from the blast pressure waves, were overturned or tilted. Trees underneath the explosion remained upright, but had their branches broken downward. B. Mass distortion of buildings. An ordinary bomb can damage only a part of a large building, which may then collapse further under the action of gravity. But the blast wave from an atomic bomb is so large that it can engulf whole buildings, no matter how great their size, pushing them over as though a giant hand had given them a shove. C. Long duration of the positive pressure pulse and consequent small effect of the negative pressure or suction phase. In any explosion, the positive pressure exerted by the blast lasts for a definite period of time, usually a small fraction of a second, and is then followed by a somewhat longer period of negative pressure or suction. The negative pressure is always much weaker than the positive, but in ordinary explosions, the short duration of the positive pulse results in many structures not having time to fail in that phase, while they are able to fail under the more extended, though weaker, negative pressure. But the duration of the positive pulse is approximately proportional to the 1/3 power of the size of the explosive charge. Thus, if the relation held true throughout the range in question. A 10-ton TNT explosion would have a positive pulse only about 1/14th as long as that of a 20,000-ton explosion. Consequently, the atomic explosions had positive pulses so much longer than those of ordinary explosives that nearly all failures probably occurred during this phase, and very little damage could be attributed to the suction which followed. One other interesting feature was the combination of flash ignition and comparative slow pressure wave. Some objects, such as thin, dry wooden slats, were ignited by the radiated flash heat, and then their fires were blown out some time later, depending on their distance from X, by the pressure blast which followed the flash radiation. Calculations of the peak pressure of the blast wave. Several ingenious methods were used by the various investigators to determine, upon visiting the wrecked cities, what had actually been the peak pressures exerted by the atomic blasts. These pressures were computed for various distances from X, and curves were then plotted which were checked against the theoretical predictions of what the pressures would be. A further check was afforded from the readings obtained by the measuring instruments which were dropped by parachute at each atomic attack. The peak pressure figures gave a direct clue to the equivalent TNT tonnage of the atomic bombs, since the pressures developed by any given amount of TNT can be calculated easily. One of the simplest methods of estimating the peak pressure is from crushing of oil drums, gasoline cans, or any other empty thin metal vessel with a small opening. The assumption made is that the blast wave pressure comes on instantaneously. The resulting pressure on the can is more than the case can withstand, and the walls collapse inward. The air inside is compressed adiabatically to such a point that the pressure inside is less, by a certain amount, than the pressure outside, this amount being the pressure difference outside and in that the walls can stand in their crumpled condition. The uncertainties involved are, first, that some air rushes in through any opening that the can may have, and thus helps to build up the pressure inside, and second, that as the pressure outside falls, the air inside cannot escape sufficiently fast to avoid the walls of the can being blown out again to some extent. These uncertainties are such that estimates of pressure based on this method are on the low side, that is, they are underestimated. Another method of calculating the peak pressure is through the bending of steel flagpoles or lightning conductors away from the explosion. It is possible to calculate the drag on a pole or rod in an airstream of a certain density and velocity. By connecting this drag with the strength of the pole in question, a determination of the pressure wave may be obtained. Still, another method of estimating the peak pressure is through the overturning of memorial stones, of which there are a great quantity in Japan. The dimensions of the stones can be used along with known data on the pressure exerted by wind against flat surfaces to calculate the desired figure. Long-range blast damage. There was no consistency in the long-range blast damage. Observers often thought they had found the limit, and then 2,000 feet farther away would find further evidence of damage. The Most impressive long-range damage was the collapse of some of the barracks sheds at Kamigo, 23,000 feet south of X in Nagasaki. It was remarkable to see some of the buildings intact to the last details, including the roof and even the windows, and yet next to them a similar building collapsed to ground level. The limiting radius for severe displacement of roof tiles in Nagasaki was about 10,000 feet, although isolated cases were found up to 16,000 feet. In Hiroshima, the general limiting radius was about 8,000 feet. However, even at a distance of 26,000 feet from X in Hiroshima, some tiles were displaced. At Mogi, 7 miles from X in Nagasaki, over steep hills, over 600 feet high, about 10% of the glass came out. In nearer sequestered localities, only 4 miles from X, no damage of any kind was caused. An interesting effect was noted at Mogi. Eyewitnesses said that they thought a raid was being made on the place. One big flash was seen, then a loud roar, followed at several second intervals by half a dozen other loud reports from all directions. These successive reports were obviously reflections from the hills surrounding Mogi. Ground shock. The ground shock in most cities was very light. Water pipes still carried water, and where leaks were visible, they were mainly above ground. Virtually all of the damage to underground utilities was caused by the collapse of buildings rather than by any direct exertion of the blast pressure. This, of course, resulted from the bombs having been exploded high in the air. Shielding or screening from blast. In any explosion, a certain amount of protection from blast may be gained by having any large and substantial object between the protected object and the center of the explosion. This shielding effect was noticeable in the atomic explosions, just as in ordinary cases, although the magnitude of the explosions and the fact that they occurred at a considerable height in the air caused marked differences from the shielding which would have characterized ordinary bomb explosions. The outstanding example of shielding was that afforded by the hills in the city of Nagasaki. It was the shielding of these hills which resulted in the smaller area of devastation in Nagasaki, despite the fact that the bomb used was not less powerful. The hills gave effective shielding only at such distances from the center of explosion that the blast pressure was becoming critical, that is, was only barely sufficient to cause collapse for the structure. Houses built in ravines in Nagasaki, pointing well away from the center of the explosion, survived without damage, but others at similar distances in ravines pointing toward the center of explosion were greatly damaged. In the north of Nagasaki, there was a small hamlet about 8,000 feet from the center of explosion. One could see a distinctive variation in the intensity of damage across the hamlet, corresponding with the shadows thrown by a sharp hill. The best example of shielding by a hill was southeast of the center of explosion in Nagasaki. The damage at 8,000 feet from X consisted of light plaster damage and destruction of about half the windows. These buildings were of European type and were on the reverse side of a steep hill. At the same distance to the south-southeast, the damage was considerably greater. That is, All windows and frames, doors, were damaged, and heavy plaster damage and cracks in the brickwork also appeared. The contrast may be illustrated also by the fact that at the Nagasaki prefectural office at 10,800 feet, the damage was bad enough for the building to be evacuated, while at the Nagasaki Normal School, to which the prefectural office had been moved, at the same distance, the damage was comparatively light. Because of the height of the bursts, no evidence was expected of the shielding of one building by another, at least up to a considerable radius. It was in fact difficult to find any evidence at any distance of such shielding. There appeared to have been a little shielding of the building behind the administration building of the torpedo works in Nagasaki, but the benefits were very slight. There was also some evidence that the group of buildings comprising the medical school in Nagasaki did afford each other mutual protection. On the whole, however, shielding of one building by another was not noticeable. There was one other peculiar type of shielding, best exhibited by the workers' houses to the north of the torpedo plant in Nagasaki. These were 6,000 to 7,000 feet north of X. The damage to these houses was not nearly as bad as those over 1,000 feet farther away from the center of explosion. It seemed as though the great destruction caused in the torpedo plant had weakened the blast a little, and the full power was not restored for another 1,000 feet or more. Flash burn. As already stated, a characteristic feature of the atomic bomb, which is quite foreign to ordinary explosives, is that a very appreciable fraction of the energy liberated goes into radiant heat and light. For a sufficiently large explosion, the flash burn produced by this radiated energy will become the dominant cause of damage, since the area of burn damage will increase in proportion to the energy released, whereas the area of blast damage increases only with the 2/3 power of the energy. Although such a reversal of the mechanism of damage was not achieved in the Hiroshima and Nagasaki bombs, the effects of the flash were, however, very evident, and many casualties resulted from flash burns. A discussion of the casualties caused by flash burns will be given later. In this section will be described the other flash effects which were observed in the two cities. The duration of the heat radiation from the bomb is so short, just a few thousandths of a second, that there is no time for the energy falling on a surface to be dissipated by thermal diffusion. The flash burn is typically a surface effect. In other words, the surface of either a person or an object exposed to the flash is raised to a very high temperature, while immediately beneath the surface very little rise in temperature occurs. The flash burning of the surface of objects, particularly wooden objects, occurred in Hiroshima up to a radius of 9,500 feet from X, and at Nagasaki, burns were visible up to 11,000 feet from X. The charring and blackening of all telephone poles, trees, and wooden posts in the areas not destroyed by the general fire occurred only on the side facing the center of explosion, and did not go around the corners of buildings or hills. The exact position of the explosion was in fact accurately determined by taking a number of sights from various objects which had been flash burned on one side only. To illustrate the effects of the flash burn, the following describes a number of examples found by an observer moving northward from the center of explosion in Nagasaki. First occurred a row of fence posts at the north edge of the prison hill, at 0.3 miles from X. The top and upper part of these posts were heavily charred. The charring on the front of the posts was sharply limited by the shadow of a wall. This wall had, however, been completely demolished by the blast, which of course arrived some time after the flash. At the north edge of the torpedo works, 1.05 miles from X, telephone poles were charred to a depth of about 0.5 millimeters. A light piece of wood, similar to the flat side of an orange crate, was found leaning against one of the telephone poles. Its front surface was charred the same way as the pole, but it was evident that it had actually been ignited. The wood was blackened through a couple of cracks and nail holes, and around the edges onto the back surface. It seemed likely that this piece of wood had flamed up under the flash for a few seconds before the flame was blown out by the wind of the blast. Farther out, between 1.05 and 1.5 miles from the explosion, were many trees and poles showing a blackening. Some of the poles had platforms near the top. The shadows cast by the platforms were clearly visible and showed that the bomb had detonated at a considerable height. The row of poles turned north and crossed the mountain ridge. The flash burn was plainly visible all the way to the top of the ridge, the farthest burn observed being at 2.0 miles from X. Another striking effect of the flash burn was the autumnal appearance of the bowl formed by the hills on three sides of the explosion point. The ridges are about 1.5 miles from X. Throughout this bowl, the foliage turned yellow, although on the far side of the ridges, the countryside was quite green. This autumnal appearance of the trees extended to about 8,000 feet from X. However, shrubs and small plants quite near the center of the explosion in Hiroshima, although stripped of leaves, had obviously not been killed. Many were throwing out new buds when observers visited the city. There are two other remarkable effects of the heat radiated from the bomb explosion. The first of these is the manner in which heat roughened the surface of polished granite, which retained its polish only where it was shielded from the radiated heat, traveling in straight lines from the explosion. This roughening of radiated heat caused the unequal expansion of the constituent crystals of the stone. For granite crystals, the melting temperature is about 600 degrees centigrade. Therefore, the depth of roughening and ultimate flaking of the granite surface indicated the depth to which this temperature occurred and helped to determine the average ground temperatures in the instant following the explosion. This effect was noted for distances about 1 1/2 times as great in Nagasaki as in Hiroshima. The second remarkable effect was the bubbling of roof tile. The size of the bubbles and their extent was proportional to their nearness to the center of explosion, and also depended on how squarely the tile itself was faced toward the explosion. The distance ratio of this effect between Nagasaki and Hiroshima was about the same as for the flaking of polished granite. Various other effects of the radiated heat were noted, including the lightening of asphalt road surfaces in spots which had not been protected from the radiated heat by any object, such as that of a person walking along the road. various other surfaces were discolored in different ways by the radiated heat. As has already been mentioned, the fact that radiant heat traveled only in straight lines from the center of explosion enabled observers to determine the direction toward the center of explosion from a number of different points by observing the shadows which were cast by intervening objects, where they shielded the otherwise exposed surface of some object. Thus the center of explosion was located with considerable accuracy. In a number of cases, these shadows also gave an indication of the height of the burst of the bomb, and occasionally a distinct penumbra was found, which enabled observers to calculate the diameter of the ball of fire at the instant it was exerting the maximum charring or burning effect. One more interesting feature connected with heat radiation was the charring of fabric to different degrees depending upon the color of the fabric. A number of instances were recorded in which persons wearing clothing of various colors received burns greatly varying in degree, the degree of burn depending upon the color of the fabric over the skin in question. For example, a shirt of alternate light and dark gray stripes, each about 1/8 of an inch wide, had the dark stripes completely burned out, but the light stripes were undamaged, and a piece of Japanese paper exposed nearly 1 1/2 miles from X had the characters, which were written in black ink, neatly burned out. End of section 5 of the atomic bombings of Hiroshima and Nagasaki.